Yes,
okay.
yes. Great.
Seems to be good. So the second talk will be given by Michael on robust tests for Gaussianity.
Yeah, small change in name. Thanks very much for having me. Thanks, Robert, for the invitation. Yeah, it's great to be here. It's also exciting to be here because it's my third work day for this place. So I'm still trying to figure out, do I have an office, where to find a transponder, and these kind of exciting questions. So yeah, so our group will be moving there over the next half year or so. So that's fun. So I want to talk to you about work on, well, that's I guess certainly also in the easier regime of things. I want to talk about testing, property testing Gaussianity, which is maybe the simplest continuous variable property you could hope to test, except for equality of states, which is yeah, good. And so that's, I guess, goes back actually to work that we did with David and Sepa. I mean, I guess there's multiple strands to this work for me personally. Yeah, it's getting late, I know. We have to get through it. So this is, for me, it goes back to work actually with David and Sepa, where we explored testing stabilizers and sort of we asked, you know, what can we do with the structure we find there and so on. And it turns out that everything's much more beautiful in the Gaussian setting, which I guess we knew, but we still didn't start that way. And then sort of there was another team that also worked on you know, learning Gaussianity and testing questions, and so we joined forces and produced something that's hopefully of interest to you. So let's see if this works. So the subject of my talk is property testing. You're already experts in it by now. Just to introduce some notation. So suppose you have a set of all quantum states, and also have to learn the laser pointer. And within that is some set of states that satisfy some property X of interest. So X is I use for the property as well as for the set. So then what we want to do is we want to design algorithms that take a certain number of copies of that state, and then decide whether, yes, our state is in that set of interest, it satisfies a property of interest, or is epsilon far from it, okay? And the goal is to do that efficiently, okay? And so natural question that many people have asked in many different settings for many, many years is which properties of classical probability distribution of quantum states can be tested efficiently? And so efficiently might mean that many things. It could mean a small number of samples or copies of the state. So that's what we'll focus on in this talk. Of course, to make it practical, you would also like to have simple circuits that realize these algorithms, where simple could mean polytime, it could mean, I don't know, short Fs, and so on and so forth. And I guess there's many reasons for studying this. I mean, it's just a fundamental question about complexity theory in a regime that's maybe a bit simpler than time complexity and usually still informative. But it's also, of course, in a sense, tells us, you know, what are the properties of many-body quantum states that we can hope to practically verify, right? If you need lots and lots of samples, then at some point you run into trouble, as we discussed, okay? And there's lots of variations here. So for example, instead of asking this yes-no question where the yes case corresponds to exactly satisfying the property, one can also study tolerant testing, where you're either pretty close or pretty far, and you can ask, you know, how small can you push the threshold between these two. You can ask, you can restrict yourself to bounded memory or to unentangled measurements. You can you know, have a different access model where you don't get copies of the state, but say you know, a reunitary that prepares the state or purification of it, and so on and so forth. Okay, so I'll study the simplest setting here. And yeah, since I claimed something about practicality, I guess many of you will know, have heard of this experiment. That's about, I guess, measuring the entanglement entropy in an actual quantum antibody system. So it's an experimental paper. And I guess they basically estimated the purity sort of in a real-life scenario. And we all know how that works, right? We do a swap test. So a super nice quantum circuit. And we know the acceptance probability is related simply to the purity of that state, right? So you're always going to accept your state if it's a pure state, and if it's sort of, let's say, constantly far from pure state, then it will reject with constant probability, okay? So that's what we call a perfectly complete test for purity. And then it would maybe be summarized as follows. People would maybe write, you know, a constant number of copies suffice to test if a state is pure or far from it, okay? And you can be more nuanced, and you could say, okay, if you want to test if it's pure or epsilon far from it, then you need a number of copies that scales. Well, somehow it depends on epsilon, say 1 over epsilon here. And for some choice of distance, this is, should be the correct number of copies. Okay, so that's useful in practice, as I guess is demonstrated by the fact that people can even do this in the laboratory. But it's also theoretically interesting, which is of interest to us. So it's, I guess, it originated, I think, among others, from a paper on quantum fingerprinting. It's closely related to a product test we'll talk about in a moment that Haro Montanaro studied. It's interesting complexity theory. So it's like the standard tool that we never think about, but it's kind of cool that it exists. Okay. All right. So here are some examples that many of you will know. Okay, and they show that sometimes we can answer these problems using a small number of copies, and sometimes we cannot. So as discussed, we can test if a state is pure or far from it using constant number of copies. And again, how do we do it? We basically take 2 copies of the state and we check if it's on a symmetric subspace. Okay, we do a swap test. Similarly, you can check if a state is a product state. Okay, I say a pure product state, because in that case, you can independently, so I guess vertically is, so A and B are the 2 subsystems of 1 copy, and the A and B on the right is another copy. So you can locally swap the A's or the B's independently, and you will still have the symmetry. Okay, and so you can just do local swap tests, pairing up every pair of subsystems, A prime, B prime, C prime, and so on. Okay, and again, the power of the test somehow does not depend on the dimensionality. I mean, the number of copies you need does not depend on dimensionality. It does not depend on the number of subsystems. So it's a cool test. But there are also bad examples. In particular, if you ask sort of the opposite question to purity testing, maximal mixedness testing, then actually you need exponentially many samples, even for constant distance. So if you want to decide whether a state is maximally mixed or 1/2 far from it, or say constantly far from it, in general you need lots of samples. Okay, and so that's a little interesting. Okay, so it's not clear, can be anywhere, and of course exponential is sort of, I mean, some power of n is always good enough because you can do tomography and then decide everything afterwards. Okay, so that's good. All right. Now, what's also interesting is that the swap test, of course, is doing an entangled measurement. You need both copies at the same time, right? And so that's not an accident. One can also study what happens when one only wants to do single copy measurements, and sometimes things become worse. Okay. And I think in a paper by Jonas and friends, I believe they study, for example, a very nuanced version of this question for purity and inner products. All right, so I guess we all love bosonic quantum systems, but so here's a little bit of pros. So I guess despite loving them, maybe we still feel most comfortable in finite dimensions when we have the circuit model to rely on, when things are, universality theorems are pretty clear and unambiguous, when complexity theory is super well developed, and while bosonic or continuous variable quantum systems are, well, very ubiquitous. I think the right sort of theory of complexity theory is still being developed, thanks to actually lots of people here in the room. And I guess we have seen this already from a customer side. So in the paper that Simon spoke about, we sort of naturally get sort of a continuous variable algorithm, and it would be super nice to have like generic tools to transform this into the circuit model, understand what needs to be done. But also on the theory building side, there will be a talk about this. Okay. And it's sort of interesting because I think in the classical world, people routinely think about designing algorithms that work with real numbers, right? If you study, I don't know, Gaussian elimination or something, then probably you first think about in a model where you just allow yourself to store arbitrary real numbers, so continuous variables. And then you later on think hard, I guess people did in the 70s, that it's even efficient if you're given your input as bit strings. Okay. And then that's sometimes also true, and often it's painful hard work, of course, to try to go there. But the original model is already very meaningful, and we sort of have an intuitive feeling for, does it work well? And then there's condition numbers and all the numeric analysis comes with it. So I wonder if we are already there, whether it's interesting to think in this direction. Okay, so maybe all this is to motivate that we want to study property testing for continuous variable systems. And I think property testing learning tasks are maybe interesting because there we can focus on sort of, coarser quantities like sample complexity, and they're already interesting because everything's infinite dimensional, and sort of it's not so clear what the right answers are. I mean, not that they are in finite dimensions, but here sort of I think it's a nice proving ground for these questions. And nevertheless, just like in the case of the swap test, one can hope that maybe the algorithms that come out, they're actually not only efficient in terms of sample complexity, but maybe they're even time efficient. Okay, and so hopefully we'll see one of these examples. Okay, so here's a little primer on Gaussian states and unitaries, which is probably on the level that people who already know it will be bored, and people who don't know it will be, I don't know, confused. So I'll try my best. So it's a sort of extremely low tech. I try, and so probably it's also a little bit wrong. But if you know how that is wrong, also you know how to fix it. So I only define now for pure states what is a Gaussian state. So for pure gates, a Gaussian state is simply a wave function. So let's say on Rn. So Hilbert space L2 of Rn. That is a Gaussian, okay, multivariate Gaussian, and it can have a complex exponent and phases and stuff, but okay, so let's take this as a definition. And so because it's a Gaussian, it's intuitive that it should be described by a mean vector by first moments and by a covariance matrix, so centered second moments, okay? And quantumly, one way to make that precise is to observe that even though we have wave function Rn, there's actually two n many natural operators, the positions and the momentum operators, so x1 to xn, p1 to pn in my notation. And then we often people just string them one after the other and call them R, so R1 to R2n, okay? And so the expectation value of those folks, which are unbounded self-adjoint operators, make up the components of the mean vector, and the covariance matrix is sort of the object, you know, where you make the thing Hermitian so that the real number comes out. So like it's like a quantum centered second moment. Okay. You can generate these things by well, Gaussian unitaries, which are basically the things that linear quantum optics allows you to do. So things like beam splitters, squeezing, evolution by quadratic Hamiltonians. If you care about pure states, then those you get from a vacuum state. Okay. Whereas the vacuum state is just the nicest Gaussian in L2Rn, the standard Gaussian. And then sort of, because the states that come out are Gaussian, you can track what happens to them simply by tracking what happens to the mean vector into the covariance matrix. Okay, so mean vector, so if you're, you know, basically the idea is that you can apply that these Gaussian unitaries, they're described by 2n by 2n matrices, not arbitrary matrices, but ones that are symplectic with respect to the natural symplectic inner product in R2n. And also displacement vector if you care about displacing things. And so the mean vector, it gets transformed in the natural way, and the covariance matrix gets also conjugated in this, you know, way that preserves positive semi-definiteness. Okay. And then one can also associate what people call phase-based distributions. So many of you will know, you know, things like characteristic functions, Wigner function, P and Q function. Those would also be Gaussians in that case. Okay. For example, yeah, they can be related to these parameters here. And these are actually 2n-dimensional Gaussian because the phase-based is 2n-dimensional. Okay, so it all fits together. So this is kind of the, it's a beautiful world that is very similar to the world of Cliffords and stabilized states, which has been elucidated by David and other folks, especially if for Qubits where D is not 2, if D is 2 is a little bit more ugly, but still can, well, I find it, okay. You may disagree. Maybe it's okay for you that 2 is 0. It's totally fine. It all works somehow, mostly. So the question we want to ask is, can one efficiently test? Okay, so that's now the precise question of the talk. If a given quantum state, a given continuous variable quantum state is Gaussian, okay, or far from it. So that's the question we want to discuss. Okay, and so it's I don't know, it's like a simple question, right? Because it's about the simplest possible continuous variable quantum states, probably that we can imagine. But it's already a little bit interesting, right? Because, well, it's maybe still not clear how to attack the problem. Okay. So to motivate one approach, so we are going to discuss two solutions. One is sort of based on symmetries, and the other is based on learning. Okay. And if there's time, we talk briefly about the lower bound. And so the one by symmetry is basically one way of sort of, you know, in sort of in a history revisionist way, coming up with a solution is by looking again at the solution for purity in product testing, and then trying to generalize. Okay. So purity testing, right? What does the swap test do? Well, essentially, it's checking that the quantum state is invariant under swaps, right? That's what it's doing. It's projecting the +1 eigenspace, symmetric subspace. Okay. So what's the point? Well, if you have an arbitrary state, then rho tensor 2, it always commutes with swaps. But if you're actually on the +1 eigenstate, that's only the case if you're a pure state. Okay, so pure tensor powers of pure states have an enhanced symmetry. Now, similarly, if you do product testing, then something is a pure product state if you can even swap locally. Okay, right? Because if it's a tensor product here, then you can exchange the A's without exchanging the B's and vice versa. Okay, and again, pure product states are singled out by this property. That's of course a stronger test than the one above because it's a more special class of states. And so in both cases, one can observe that the states of interest, pure states or pure product states, they form a single orbit under a certain group. That will come back later. You can already think about, Gaussian states are from an orbit under the Gaussian unitaries. If you look at already two copies of the state, they have an enhanced symmetry as opposed to the naive guess, as opposed to if you took a random state, for example, a random mixed state, but according to some distribution, or a random pure state according to the unique distribution that we always look at. So that invariance, this enhanced symmetry gives rise to a natural test. Just measure the corresponding operator, okay? Like a swap or local swaps or global swaps. And in both of these cases, as we discussed, it's true that the corresponding test is robust. So, you know, if you accept this high probability, you're close to a state from the special class. But it's not fully obvious. One has to do a little analysis. Okay, it's like not super hard in these cases, but one has to think. And just observe, right? If you look at a smaller group, then of course you get fewer states. You can hope for more symmetry, right? Pure product states are a subset of all pure states, so they have more. They can possibly have more symmetry. All right, so now let's discuss the symmetry of Gaussians, and let's forget quantum for a moment. Let's just look at probability distributions, okay? So suppose you have okay, this is terrible notation. X is now a Gaussian random variable and no longer a set of states of interest. If X is a Gaussian with mean vector mu and covariance matrix sigma, okay, here are two facts that we know. We know what happens when we apply linear transformations. Well, the mean vector gets multiplied by the linear map, invertible linear map L, if you like, and the covariance matrix gets conjugated by LL transpose, okay? The other thing that we know is that if you take t copies, t IID copies of a Gaussian, then that's a random vector, which itself is Gaussian. It's a multivariate Gaussian. Okay, and if you start with a multivariate Gaussian of n in n dimensions, and you take t IID copies, then you get a Gaussian distribution of n times t many things. And the covariance matrix, if you write it down, is simply the tensor product of the original covariance matrix with an identity matrix. And the mean vector similarly gets multiplied with the all ones vectors. It's the same mean for every copy. Okay. So if we combine these two facts, we see that t copies of a Gaussian probability of a Gaussian random variable have an enhanced symmetry. You can not only swap these IID copies, which you could do with IID copies in arbitrary distribution, but you can sort of rotate them, right? You could rotate them at an arbitrary continuous angle. Why is that? Well, if you do nothing on, if you treat all the modes the same, all the dimensions of your single copy vector, but you rotate among the t copies, so to say, in the in the R to the t, then this OO transpose is the identity, right? It commutes with the identity. Okay. So t copies of Gaussian random variable have an enhanced symmetry, and actually Gaussians are characterized by this way. Okay. And so so the enhanced symmetry, to be more precise, right, is that whereas for TID copies of an arbitrary random variable, we just have a permutation symmetry. For Gaussians, we can apply an arbitrary orthogonal matrix sort of that treats the whole individual random vectors, all the same. So it's like, yeah. So and okay, if they have a mean vector, of course, the mean should also be preserved. So this all ones vector needs to be preserved. In other words, it should be a stochastic orthogonal matrix. Okay. Cool. And actually, even a 45-degree rotation is enough. So in the centered case, so if you have a mean zero Gaussian, you just take a non-trivial rotation, for example, such that xy goes to x plus y, x minus y, or minus x plus y if you like rotations, over root 2. Okay, and sort of if you're invariant under this, so if you have two copies, two ID copies of a random variable, and it has the symmetry, it must be centered Gaussian. Okay. Cool. And then I guess variants of the statement, I mean, this is like very well-known variants of the statement, for example, known as the Katz-Bernstein theorem and its generalizations. There's a Definetti theorem by Diaconis for multivariate normal distributions, which also sort of relies on this. It's like the usual Definetti thing, where you say, oh, if you have a certain symmetry and you trace out, then your mixture of Definetti states. Here, your Definetti states with individual Gaussian. Okay. All right. Cool. These are also quantum facts. Okay, so I explained them for you for classical probability distributions, but actually the same, everything that's written here can be translated into quantum language. I mean, I'm a little bit imprecise now about, we still have time, about mixed versus pure states and so on, but I think that's okay. All right. So here's the quantum fact again that we need. So a pure state is Gaussian if and only if you take two copies of it, then you're invariant under stochastic if you want rotation. Sorry, if you take t copies of it, there's a typo, not two. If you take t copies of it, you're invariant under stochastic orthogonal transformations that sort of rotate between the t copies. And if you want to think about it very concretely, right, you can take a single copy Hilbert space, which consists of n modes. You take t tensor copies. You can think of this as wave functions on a space of matrices, and then if you multiply the coordinates by the orthogonal matrix, that's really the action that's happening. Okay. So there's an OT, a continuous action here. Okay, and so I mentioned many works here from which this result can be extracted. I think it's sort of folklore, well known. I think the earliest one we found, I think, is a paper by Springard al. from a year that I forget. I think one can extract it from Gaussian extremality type results by equality condition for entropy power inequality. It's very closely related to the math that Antony used in his Gaussian quantum definity works. There are proposals for robust version of the statement, which is of course extremely relevant for us, but it appears from looking at the bounds, they get there exponentially bad. So I think what I'll tell you in a moment is still interesting. And then also more recent works where the same test was proposed, but there's no really robust analysis, okay? One can also just do a hands-on calculation and check, what does it mean to be rotation variant and do a bit of yoga and then get out that it must be Gaussians, okay? Cool. So in particular, even the 45 degrees would be enough, which means kind of, put your thing through a 50-50 beam splitter and check that what comes out is the same that you came in. That would be a 4-copy test. Alternatively, you can also just project on the rotation variant subspace, at least in theory. Okay. All right, and so what we do is we show that this gives rise to an efficient test in the sense that we can really say how many copies you need to decide between is it a Gaussian state or epsilon far from it, and where n is the number of modes and e is something like the energy per mode. We do use a quadratic version of the energy, which is natural here, but maybe it's too technical for this hour. And if we care about testing whether we mean zero Gaussian state, then the natural test uses 2 copies, because O2 is an interesting group. If we want to test general Gaussianity, not necessarily mean zero, then we can use 3 ones where there's interesting stochastic rotations, so rotations that preserve the all ones vector. Okay. Cool. Right. Yeah, and I guess I gave you a toy version of the result. We also have this tolerant testing. We also consider tolerant testing where you have 2 thresholds, epsilon A close or epsilon B far, but somehow the bounds are not beautiful enough to be allowed to put on the slides. Okay. I want to give you maybe some intuition why the result should be true, but it's very sketchy, but maybe it's still interesting. So, so the intuition is as follows: if you're rotation variant, but then it means that if you look at you're in the kernel of the generator of the rotation action, right? And if you write down the generator, it looks something like x tensor p minus p tensor x. Okay, maybe with an I, depending on your taste. So if you have a quantum state and the expectation value of g squared is 0, then and only then it's a Gaussian state. Okay, and sort of intuitively, this number being small means that the test accepts with high probability. Okay. Now, on the other hand, you can actually compute what happens when you compute g squared. And why g squared is sort of quartic and x and p? It turns out that if you evaluate this expression in a product state, actually it's going to be a product of quadratic things. So you can hope to express it all in terms of covariance matrices. Okay? And in particular, if you this rotation test by design is invariant under Gaussian unitaries, so you can always, and maybe that's a comment for the experts, diagonalize your covariance matrix by symplectic transformation. Okay, and if you do so, then what you find is that the expectation value of the second moment of the generator is basically just the expectation value squared of harmonic oscillator minus its ground state energy. Okay, and so this thing is largely equal to 0, and the harmonic oscillator is gapped. So if this is a small number, if this number is close to 0, then this guy is close to the ground state energy, so the state has good overlap with the ground state, which is a Gaussian state. Okay, standard Gaussian state. Okay, so that's like some intuition for how one could analyze something like that. All right, yoga of the commutant. What did I mean? Right, exactly. So, so I think I was already alluding towards this before. So there's some very nice structure here that worked in all the examples we discussed so far. Namely, there's a group G, could be the group of Gaussian unitaries, could be the whole unitary group, could be the local unitary group that acts on what we call a single copy, not single mode, the single copy Hilbert space. And the property of interest is G invariant. Okay, and in this case, it's natural. And if you look at an invariant, figure of merit, it is true that you can take the optimal test given T copies as an element, or the P of M element, the exacting P of M element, as an element in the commutant of the Tth tensor power action of this group. Okay, so In other words, if your group G acts on the single copy Hilbert space H, then G also acts on the T copy Hilbert space by G to the tensor T. Okay? And the commutant are all the operators that commute with this. And so it's natural to look there, and also sort of without loss of generality to look there for good tests. Okay? And now in the cases of interest, it turned out that this commutant was also generated by group action, and we're basically measuring the invariance of, under an interesting element there. Okay, because I guess we saw that, right? Sort of. Like it's sort of plausible, right, that if you took a random element from the commutant, then probably it's tailored towards the states of interest, okay? And now, of course, random elements are not so nice, well, they're nice to analyze, but then not if you really want deterministic results like we do here. But it still gives us good guesses, right? For example, if the commutant is generated by permutations, well, we take the one non-trivial permutation, right? If it's generated by rotations, T by T rotations, then let's pick a rotation that's not a permutation, right? So this kind of advice, this kind of idea, okay? And so as I was saying, right, for purity and product testing, the action is, U to the tensor T or UA to tensor UB to the tensor T, and then the corresponding commutants are, is spanned by the symmetric group. I guess precisely I only wrote on the purity case here, and that is something everyone knows, right? It's just a statement of show biduality. And similarly, in this Gaussian case, the commutant of T powers of Gaussian unitaries that is generated by the action of an orthogonal group. That's something that's known as Kashiwara-Vernia / and Howard duality. Okay, and there's a similar story for fermions as well, right? Where kind of you have a spin action, sort of Gaussian unities are spin instead of symplectic, and a similar story. Okay, so that's cool. And actually, so now I can maybe clarify my comment on the title slide. So the same strategy actually also works for the, let's say, finite dimensional colleagues of Gaussian states, stabilizer states, and the corresponding dynamics being the Clifford unitaries. So there in a in a paper with David and Sepa, we worked out this commutant in the relevant regime of interest, and we could show, for example, that stabilized testing is possible using constantly many copies. Okay, so this was like an open problem. So the interesting thing is that here the number of copies needed did not even depend on the number of modes, the number of qubits. That's better than what we achieved in the Gaussian case, right? We had just dependence on n. Right, and that somehow found surprisingly many applications, and there's these nice further developments to, I guess, to the general setting where you look at an arbitrary moment relative to the number of qubits. And I like both from, like lower bounds on quantum pseudo-randomness and, many body systems where people study their statistics. So, one could hope that maybe this general picture, which is mathematically fully understood since the 80s, could also be useful for these analyses. Okay, and I guess also Ni's cool paper is also sort of in this instance, right, where he really shows how to use this machinery to do something cool for quantum information. Okay, so that was the yoga of the commutant. I think 5 minutes, 0 minutes. So I think we started kind of 10 minutes later. Do you know? Close to 0 more? Sounds good. This is a 25-minute 0, right? Good. Very good. Yeah, we're on slide 11 of 13, so I think we'll just be good. So I just want to say briefly, you can also do unentangled measurements. That is where the strategy of the other folks came in, because they had recently, before that, written a paper where they discussed how to do tomography of the covariance matrix. And it turns out that Gaussian quantum states can be characterized in many ways. And one of them that I did not mention is that they're minimal uncertainty in a certain precise sense. Okay, namely, if you look at the symplectic eigenvalues of the covariance matrix, then they are always at least 1. That's the uncertainty principle. They're exactly 1 if and only if the state is Gaussian. Okay, so the strategy, roughly speaking, there is you do tomography using simple single copy measurements known as homodyne measurements, and then you just check if the symplectic eigenvalues are 1, and then you can do it, and you get a scaling that's worse than epsilon and still poly in E and N. Okay, so that's kind of a complementary result. And it's sort of similar, an analogy as in the stabilizer world. There we know that order n, where n is the number of qubits copies, are enough if you do unentangled measurements, and you need at least square root of n. So there's some dependence on number of modes, which is not there if you do entangled measurements, which I think is interesting. And it begs the question, which is maybe the last question, whether that's also possible in a Gaussian case, right? Can we somehow give a test that only depends, let's say, on an energy per mode bound, but not on the number of modes, so maybe on nothing at all? And confusingly enough, we have some partial results. If you're close enough, then it's true. But we cannot really handle the case where you're far, which seems paradoxical, but still hard. Okay. And then there's also a lower bound that says that in the case of mixed states, which there was carefully to avoid so far, somehow things are really hard. You need many copies to test mixed Gaussianity, but I also didn't define to you what mixed Gaussian states are, so that's not something to discuss today. All right, so let me summarize. So we discussed property testing, which is, I guess, motivated by quantum information processing in the near term, is that? But also by, I think, cool quantum TCS questions. For Gaussian states, which I think is interesting also because things are infinite dimensional, so we can revisit some of the tools that we know. Some of the tools we do know, like Chauval duality, they generalize nicely, and accordingly, one can also develop new, cool tests. And so maybe these techniques and also the learning theory techniques that I could not really give justice on the second to last slide might also be useful for other works. Okay, so yeah, thanks very much.
Questions for Michael?
What you basically need is you need to rotate aka passive optics and then look at projections into phase space aka homodyne. And I'm asking this because some years ago we did some theorist quad work for a team in Hamburg, preparing bound entangled states. And these states were idiotic confidence bound entangled, 3 sigma or something or more, under the condition that the states are Gaussian. Then we did some Bohrmann's tests of Gaussianity of kind that what we could do. Yep. But I mean, then the question is, can you uplift this to a proper Gaussianity test? Because then you would really get a huge state preparation result. Maybe possibly based on existing data.
That's very interesting. Let's definitely talk about it. Yeah, I mean, it could be that depending on what the existing data is, maybe the unentangled measurement result, which is maybe the more practically relevant. But indeed, I mean, the other one is basically, I mean, there's different options, but so the first approach, which is theoretically more efficient, it's sort of a simple circuit, but you still need entangled measurements, right? So you need at least 2, and then you have to do this rotation variance test, which is not 100% clear, or you do 4, and then you do, but then it's just linear optics afterwards, yeah. It's like linear optics and parity.
Because the existing data is entangled measurements, but just a beam splitter or something, and then
yeah, it sounds maybe actually, yeah. Let's definitely chat about this. It's very interesting. Yeah. So it's really linear optics doing a kind of a bosonic swap test, if you want. Yeah.
I'm wondering what your conjecture is about the energy independence. What the answer is? You didn't say.
No, I also don't know. So I feel I mean about the mode. I feel like if you had some energy bound per mode, then I would feel at least we should be able to get rid of the scaling with the number of modes. That I would think I would feel optimistic about. Also in the fermionic case, that such a result could be true. But yeah, I don't know. I don't wager it. Yes.
It's a slightly different problem. If you're promised that you're Gaussian, but it's you want to learn a Gaussian, that you have to do in a basically energy independent way with a log E dependence. So that works. It's not quite the same problem, but almost.
Yeah, I don't dare making a prediction. Yeah. Yeah, there's lots of interesting not little, but lots of interesting, I think questions where it really feels we are the limitations also of techniques. So for example, analyzing this 45-degree rotation test, which seems like the nicest test, in the same robust way, again, is something we are struggling in general, and it feels we should not be. So ideas, I think, are very welcome. Yeah.
There's one last quick question. Take it. Yes.
Sorry, just maybe I was wrong. So did you develop along the way Chauval duality for fermionic linear optics, or
So,
yeah,
very good. Yeah, good question. So there is such a thing, and it's this Howard-Kashiwara-Vernier duality. Typically, what they do is they do just a symplectic group without an affine part, and the commutant there, but you can easily add the displacements, and then you get the stochastic condition if you want. It's also very explicit in paper, so really, people really understand the decomposition, and we in the paper that will appear by October 10, we give a precise citation of that as well. And so in this Kashiwara-Verney paper, for example, they really tell, you know, what are the Young diagrams, what are the highest weights, what is matched up. It turned out here, in the analysis, we didn't really need to rely on these results. It's more like gave the framework. But for example, if you asked, if you asked more nuanced questions, right? I mean, or if you, I mean, one thing I don't want to say on record is, you know, if you did a symplectic spectrum estimation, probably the measurement is clear. And so that's something we would really love to analyze in the next step. Yeah. Thanks.
So now we'll have some lightning talks for the posters.